Hello Year 10. This is the final lesson in the work that we've been doing on volume and surface area. And in this lesson we're going to apply our knowledge of the volume and surface area of cones to a special 3D shape. If I take any cone and cut parallel to the base of the cone, I end up with two pieces. A small cone, which is mathematically similar to the larger one, and this piece on the bottom, which is called a frustum, the bit that's left after you've cut the other cone off. So as I'm sure you can see, if I wanted to find the volume of the frustum, I take the volume of the large cone and I subtract the volume of the smaller cone. It's relatively straightforward when you see it like that, but it can be a little bit more complicated when you see it as it is in example 1. So, example 1 says, find the volume and surface area of this frustum. So in order to find the volume of the frustum, we need to know the volume of the original cone and the volume of the small cone, neither of which we can see. But we do know something about them. We know that the radius of the small cone is 8 and the radius of the large cone is 12. So I'm going to imagine the cone as it would have been, like that. We can focus. There it is. Now we know that these two cones are mathematically similar, so I'm going to generate some similar triangles which will help me find the other lengths that I need. So taking a cut or a line straight down there from the centre of the big circle through the centre of the small circle right up to the point of the cone gives me a large right angle triangle that looks like this, where that is 12. And doing the same for the small cone, I end up with this. A similar triangle where that is 8. Now we do know that that gap there, that distance there from there to there is 5. But we don't know anything else, so I'm going to call this H. And this one obviously must be H plus 5. H plus 5. And now I'm going to use my similar triangles to set up an equation. So the ratio of that side to that side must be equal to the ratio of that side to that side because they are similar. So H plus 5 over 12 is equal to H over 8. Timesing both sides by 8 and timesing both sides by 12 gives me 8 lots of H plus 5 is equal to 12 lots of H. And then I just need to multiply out and solve the equation. So 8H plus 40 is equal to 12H. So 4H is equal to 40, which means that H is equal to 10. Which means I now know the height of my small cone is 10 and the height of my large cone is 15. So, quickly redrawing those cones. Not the world's greatest sketch, but gives you an idea. We know that this here is 10 and then this here is 15. So the volume of the large cone is going to be equal to 1/3 pi r squared h for the large cone, which would be 1/3 times by pi times by 12 squared times by 15. Simplifying that gives me 720 pi. Let's leave it like that so we don't have to worry about any rounding. The volume of the small cone, same formula, but this time the radius is 8 squared, radius squared I should say is 8 squared, and the height is 10, which gives me, when I simplify that, 640 over 3 pi. So the volume of the frustum is going to be the large cone, subtract the volume of the small cone, which is 720 pi, take away 640 over 3 pi, and if we were doing this without a calculator we could leave it in terms of pi, but for now put that into your calculator and that comes out as 1591.74 ... So let's go for the nearest whole number, or 4 significant figures, and that's 1592 cubic centimeters, because it's a volume. So there's the volume of the frustum. The surface area of the frustum can be found in the same sort of way. We know that the surface area consists of, let's just quickly sketch it again. We have got here the curved surface area around there, and we've got two circles, a small circle on the top and a larger circle on the bottom. Now the curved surface area we find in the same way as we did with the volume. However, we know that we need the slant height, that's side L, the slopey side of the cone, and we don't have that. But we do have some right angle triangles, which means we can go back to using Pythagoras. So for the large cone, we know that that was 12. This one was h plus 5, so that becomes 15, and that's the slant height of the large cone. So L squared is equal to 12 squared plus 15 squared. So that's 144 plus 225 gives me that L is equal to the root of 369, and I'm going to leave it like that. The smaller cone, again going back to that right angled triangle, that was 8, that was 10, and the slant height for this triangle is going to be L squared is equal to 8 squared plus 10 squared, so 64 and 100, so L is going to be the square root of 164, so that's the slant height of the smaller cone. So curved surface area of the large cone. Pi RL for the curved surface area, and for the large cone that will be pi times by 12 times by the root of 369, which we're going to write as 12 pi root 369, its exact value. The curved surface area for the smaller cone is exactly the same formula, pi RL, but for the small cone it's going to be pi times by 8 times by the root of 164, which is 8 pi root 164. So I now have all the bits that I need. A total surface area of the frustum is going to be equal to the area of the top circle plus the area of the bottom circle, or the base circle, plus the curved surface area. So in our case that is going to be, the radius of the top circle is 8, so that's pi times by 8 squared. The radius of the base circle is 12, pi times by 12 squared. And the curved surface area was the big surface area, take the small surface area. So 12 pi, root 369, take away 8 pi, root 164. So there's my three components: top circle, bottom circle, curved surface area. 64 pi plus 144 pi plus 12 pi, root 369, take away 8 pi, root 164. If I wanted to, I could simplify it even further and make that 208 pi, but I'm just going to stick it all into my calculator, and it comes out as 1055.771, etc., which to the nearest whole number or to 4 significant figures is 1056 square centimetres. Okay, as I said, in principle quite straightforward. Small cone take, a large cone take away small cone, but in reality can be a little bit more complicated and uses several other techniques such as similar triangles and Pythagoras. Right, now it's your turn, and you should have a go at questions in exercise 15.3a, which you'll find on page 315.